Mr. Dudley Ortecho.
And I'm Tim Helmer.
And today we're going to be talking to you about the beacon and optical navigation for an autonomous rover.
So our mentor was Maurice Willis III.
And our collaborating researchers were Cassandra Spath and Josh Beatty.
So the quote from 2014 FSI is by Edwin Hubble, is equipped with his 5 senses. Man goes out and explores the universe around him, and he calls the adventure science. Our project is going to tie into this quote by giving our robot senses to explore the universe around it.
So a little bit about the challenge. It was issued by the Colorado Space Grant Consortium, and it involves navigating an arena-like place where there will be many obstacles such as cardboard boxes, rocks, holes, logs, all sorts of things that our robot has to avoid. And the ending point is a beacon, as shown here. The beacon sends a frequency out to the robot and senses where it is in the world. So it's like a higher frequency would be it's closer. So a couple of the requirements for the robot, it has to be under 4 kilograms, about 8.8 pounds, and it has to be under $500. It has to be completely autonomous. Autonomous meaning a human cannot interact with it whatsoever. So no controllers, no picking it up and moving it. It has to do all the thinking by itself.
So just a little bit even more about our project. We had to build, the robot. So there's the 3 main components to building this robot. There's the mechanical engineering side of it, the software engineering side of it, and the documentation of it. So me and Dudley are part of the mechanical engineering side of this robot. So we had to find and fill needs that this robot had. So when we start, we had to find sensors to go on it, and then we had to design mounts for it and make those mounts. And then all along the way we had to document our ideas by using pictures, and we had a notebook that we wrote down in every day so we could see how our ideas progressed into the final product.
So let's talk about a little bit about the chassis. The chassis is the body of the robot along with the wheels and what controls it. So this chassis, the metal part of it, was made by a previous project called the Lazarus Project here at UNC, made by Robert Sheely in 2012. What he made was a project that he hoped that in the future other projects would build off of and create something better than what he did, and that's something that we plan to do. So modifications obviously had to be made, and a couple of them are.
So we had to, once we found sensors that would work for our needs, we had to find out how to attach them to the robot. So the way we did that, we got our notebook out, we drew ideas. Once we finally thought of a good idea, we went and used a program called Creo 2.0, and we created a CAD, or computer-aided design model, on the computer, which converted into a file that the MakerBot Replicator 2 3D printer could print out for us. And when that was printed, we had to attach it to the robot. So here, we just drilled holes in the top plate, as you can see there. And then we bolted on all the mounts for the sensors, as well as attaching the sensors to the mounts themselves.
So a little bit about the electronic side of the robot. What we mainly used as a brain was an Arduino Uno. So we had to plan everything out from the beginning, knowing where the electronics go, what connects to what, where the power will go versus where the ground will go. So how the Arduino works is through input and output, just like a computer does, binary code, 1s and 0s. So what it does, it receives information from the sensors saying, oh look, there's power now, saying, oh look, there's a wall. So it has to tell the motors, back up, turn a bit, and move away from the obstacle. We all did this using electronics, both using soldering, which is a technique where you take a metal alloy, melt it down, and connect wires either to the Arduino Uno, to themselves, or to the chassis of the robot. And so to program this, which was the other team, Cassandra and Josh, they had to use a version of C++, which Arduino provides, to map out how each sensor will function with with the motors.
So the first sensor that we are trying to implement here is the ultrasonic sensor. Now the ultrasonic sensor is similar to sonar, and it's formerly known as the parallax ping sensor. It emits a wave of 40 kilohertz, and just for reference, humans can only hear up to 20 kilohertz. And so what it does is it sends out a wave, and then whatever bounces back, it takes the time it takes for it to bounce back, and it can judge distance by that. So usually, like traditionally, this sensor is used to face forward on a robot, but since we have the two about to be mentioned bump sensors, we are facing it down so that it can detect any drastic changes in elevation of the ground in front of the actual robot. So this can prevent it from going down anything too steep that it would not be able to handle, to where it would probably flip over and turtle, which is if it flips over on its back and so it can't move anywhere. And it will also avoid high centering. If it gets on a bump of land and none of the wheels can touch the ground, then it couldn't go anywhere from there.
So the bump switches, or limit switches as they're properly called, are the switches mounted here on the front. There's two in the front used to detect what is right and what is left of the robot. And they work by either making a circuit or by breaking a circuit. What we're using them right now for is making a circuit. So as shown in the diagram up above, these little connections here are the limit switches themselves. Power goes to a pin, but once the limit switch is turned on, the power instead is diverted into the ground, so pin doesn't receive any more power, hence the 1 meaning it's connected and 0 meaning it's not connected. We use this as a digital stop, so it knows when a wall was hit because the limit switch made a circuit, and the Arduino interprets that and says, well, the robot stopped and turned back. It is also used as a mechanical mount, meaning that physically stops the robot from moving forward and using its own inertia against itself by absorbing all the trauma that it experiences. So it uses this by having more mass than the ultrasonic sensor does, so it absorbs more of the trauma, as well as having two limit switches in front, which helps distribute the force better.
So the logic behind these, as he kind of mentioned, there's a left and right one. So what happens is they are wired up so that they cross, the bumpers actually cross each other, so that when the left one gets hit, when the right one gets hit, it's actually on the left side, so the Arduino just has to flip it around.
So the results of the experiment was, it's currently running as planned, sort of, but it does have some technical issues with the sensors themselves. It sometimes gets stuck in certain areas. It sometimes just stops functioning. We are trying to get these fixed, obviously, so that others could use this as their own platform. So the bump sensors are the only thing that are operational at the current point, but we really hope to integrate the ultrasonic sensors so that it could see the height for holes and things that are too high, as well as the beacon tracker that will receive the transmission from the beacon itself.
So as you can see here, the robot's just going along, nothing in its way, and then something comes up, it hits one of the bump sensors, which tells the Arduino inside of it to back up, turn 45 degrees, and go somewhere else. So it hits something else, it does the exact same thing. So what we didn't mention earlier is that when it hits the left side, it turns to the right because there has to be something on the left side for it to hit. So that's the reason that does that. So this is an example of how the engineering side of this had to talk to the software engineering side, because in programming, the turning of this is calculated in milliseconds, but not in degrees. So we had to time how many milliseconds it took for it to turn a certain amount of degrees. Now here, it has hit the leg of the chair, but it has not tripped any of the bump sensors until that point. So by that is definitely one issue, that the bumpers are not completely inclusive of everywhere in front.
So the conclusion of the robot, much like the Lazarus project that it was built off of, we hope to create something that future FSIers or people who attend UNC could use so they could navigate around the world or extraterrestrial planets. So a couple applications of this robot can be navigating Mars, say, or other planets and extraterrestrial bodies, as well as go out into the field here on Earth, excavating demolished buildings, seeing if there's anybody still alive, or any possible things that we could salvage.
And so, I forgot to do it after the video, we will give you a little demo, just because you saw in the video, but you can see it live. So to power up the motor controllers, there's two of them, one for each pair of wheels, and then power up the Arduino. The code now is to go really slow, so in case anything does hit, it won't break anything. So I'll press one of the bump sensors, turn into something, stops, backs up, turns 45 degrees, and continues going. It goes on the other side, stops, backs up, and keeps going. So here's just a few of the references we use to help us along in our project. And so I would like to thank the Adolf Force Foundation for funding me to be here at FSI this year. It has really been a great experience, just overall. I could not have spent my summer anywhere else and had as much fun as I did. And also for my research, I'd like to thank the Bacon Family Foundation for helping me with that, because with their funding, we have built part of this.
Personally, I would like to thank Brian Kanaga for his money. He's a FSI alumni from the class of 1984, and he really helped me to come here to FSI and sponsor me in attending this really, really fun event, and I personally thank him a lot for it. I would also like to thank the Kinder Morgan Foundation for also spending money and funding us for this research project on this robot. They really helped us out a lot in this robot, and it was a really fun experience.
And also, we would like to just take a moment to thank the UNC Physics Department for allowing us to use their labs and materials, and their professors, actually, to help us along our way.
As well as anyone at FSI, such as Lori Ball, Chris, Jessica, and any other staff that really helped us along the way.
Thank you very much.